Good morning, everyone. I hope you're well where you are and ready for the second in our series of lectures on an introduction to radio astronomy. This lecture for today is intended to give you some introduction to the field of astronomy, to familiarize it with its history as a field of study, and to introduce to you some of the basic questions that radio astronomy seeks to answer. And then finally, we're going to introduce some basic concepts of radio waves and their measurement that will be important for us going forward. So this lecture is divided into three sections. First, I'm going to give you a very broad overview of the history of radio astronomy as it developed. Then I'm going to introduce some of the fundamental questions of radio astronomy, why we have such a thing as radio astronomy, and then finally do some basics of radiation. Right, so radio astronomy has its beginnings all the way back in the 19th century, starting with James Clerk Maxwell. Maxwell was a Scottish scientist. He's known as the second great unifier of physics after Isaac Newton. Isaac Newton unified the force of gravity with the movement of celestial objects. Maxwell unified the forces of electricity and magnetism. So at that stage, electricity and magnetism were both phenomena that had been studied by physicists before. They had a pretty good description for them, but they didn't tie them into one another. They didn't realize that they were part of the same phenomenon. So what Maxwell did was he wrote his very famous Maxwell equations. I'm sure you'll be familiar with them already. It's a set of four differential equations that together describes, at least on a macroscopic level, precisely the behavior of electric and magnetic fields, as well as current. And that was very important in illustrating a new conception of these two forces as two aspects of the same underlying force of electromagnetism. And so to this day, a big project in physics is to unify different forces and to get some grand unified theory. And Newton and Maxwell kind of started that process off. Another very important consequence of Maxwell's equations was that the general solution to them, as you can see the equations on the left, they describe plane waves, electric and magnetic fields oscillating perpendicular to one another and traveling at a speed of 3 times 10 to the power 8 meters per second. And at that stage, they already knew that that was exactly the speed of light. So this confirmed to them that, in fact, light existed as a traveling electromagnetic wave. So it was a completely different description of light up to that point, and it opened up a lot of doors, including the notion that since it's an oscillating wave, it can oscillate with different frequencies, and there might be frequencies of light beyond what we are able to see with our naked eyes. The next big intervention in the study of radio waves came from Heinrich Hertz. He was a German PhD student of Hermann von Helmholtz. And his PhD project was to try to prove the existence of these electromagnetic waves. And to do that, he built what he called a spark gap transmitter. So on the bottom of the screen, there's a picture of his spark gap transmitter. And it's basically just two long wires, a meter long each, connected to some conducting spheres at the end. And when he applied an electric current to those wires, because there's a short gap between them, they formed a spark between those two ends of the wires. And that spark formed a standing wave, which oscillated in the radio regime. Um, for the record, I can't see the chat or anything, so if you have any questions or something, you'll have to speak up. So that was his transmit. That was just to create this gap with a certain spark gap with a certain wavelength associated with it. And then when he held up his receiver, was just a wire bent into a circle with a gap the same length as the gap in the transmitter. When he held it up to the transmitter, he found that there was also another gap, also another spark in the receiver. So thereby proving that he had transmitted some electromagnetic wave and proving the existence of electromagnetic waves. The next big innovator in radio science was an Italian electrical engineer called Guglielmo Marconi. I believe that's close to the pronunciation. And he pioneered something called radio telegraphy, which basically meant sending telegraph messages via a radio emission. So he greatly improved on transmitter and receiver technology to the point that by 1901, they could do long distance instant communication. In 1901 was the first year that they transmitted a message from the UK to Canada. And in 1909, he won a Nobel Prize for that work, along with Carl Brown. The next big important discovery in the field of radio waves came from Max Planck. And this was partly in response to the fact that nobody had been able to detect radio waves from celestial objects at that point. So various people had tried to point radio receivers to the sun and to the planets, but kind of unexpectedly, nobody could receive any radio signals from those sources, and that was a kind of a big mystery at the time. And another mystery was what they called the ultraviolet catastrophe. That was to do with the frequency dependence of spectral radiance. According to classical theory, as you can see on the black line on this plot, the prediction from classical theory from the Rayleigh-Jeans law was that the spectral radiance should continue increasing indefinitely to shorter and shorter wavelengths, so that at the very short wavelengths, including at visible light, the spectral radiance should be infinite, which is a problem because you can't have infinite energy. So Planck solved this problem by developing his theory of black body radiation, including the quantization of energy. So for the first time, he conceived of electromagnetic radiation not as continuous, but as consisting of discrete quanta, what we now know of as photons. And according to his Planck distribution, he showed that the distribution of spectral radiance according to wavelength displays this kind of bell-shaped curve, as you can see in the plot, with the peak of it changing depending on the temperature of the black body emitter. So one very important consequence of this theory was that in order to get radio wavelength emission, from a black body, so that's about centimeters, on the order of centimeters, you would have to have an emitter that's at very, very low temperatures. Um, so um, so that just explained why they couldn't see any radio emission from the sun, from the planets. And for a long time after that, for um, probably the first 3 decades of the 20th century, people just gave up on looking for radio waves in the sky. That changed with Karl Jansky. He was a radio engineer at Bell Telephone Laboratories. In 1928, he was tasked with investigating interference in wireless communication, trying to see what kind of emission from the sky might be causing interference in communication. So he built on the laboratory grounds, he built what's called Jansky's merry-go-round, which is this setup of a range of radio antennas set up on a rotating disc. You can see a replica of it here at the bottom. And so he would turn his merry-go-round slowly and try to observe different parts of the sky at about 20 megahertz. And he did that for many months. He was able to distinguish between different sources of noise in communications. He could see what was from man-made interference, what was from lightning, all of that. But he found in his data there was one specific source of static that he could not account for. And very interestingly, that source of noise was fluctuating, repeating, going up and down more or less every day. And so once he'd observed for long enough to determine the precise period, he found that the period was exactly 23 hours and 56 minutes, which is exactly the length of a sidereal day, meaning that this unknown signal must be coming from some point in space. And soon he found that the signal was strongest from the center of the Milky Way. So we now know that he was actually pointing towards the supermassive black hole at the center of our galaxy, Sagittarius A star. This was the first detection of extraterrestrial radio waves, and therefore we call Jansky the father of radio astronomy. However, his discovery was largely ignored, at least by the academic establishment, for a few reasons. First of which was Jansky was an engineer, not a scientist, so there was a bit of professional rivalry, you might say. Second, Jansky died young, only 45 years old. He died of a heart defect, so he wasn't able to continue his work. But then probably the biggest reason why radio astronomy stagnated for a while was because it was the Great Depression in the US, and there was just no funding for anybody who wanted to look for radio waves from the sky. So the flame of radio astronomy wasn't held up by astronomers. It was actually continued by an amateur radio enthusiast with the wonderful name of Grote Reber. He was an electrical engineer who read Jansky's work and was very inspired. He tried to get a job at Bell Laboratories, but was unsuccessful. And so in 1937, he decided, okay, I'm going to build my own telescope in my backyard. So in his little backyard in a small town in Illinois, he built the world's first parabolic reflector, this 9-meter parabolic reflector, which looks very much like a modern day radio telescope, all built by hand. And so in 1941 to 43, he conducted the first radio survey of the sky, all from his backyard, producing these wonderful contour maps of radio emission from the sky. And so that's why we say Jansky might have been the father of radio astronomy, but the first real radio astronomer was Grote Reber. And the next big figure in the history of radio astronomy is an Australian called Joseph Pawsey. He's known as the father of Australian radio astronomy. And he's very important for introducing the concept of interferometry to radio observations. So he pioneered a technique called sea interferometry. In the middle plot here, you can see they basically set up a big radio receiver looking over some cliffs nearby Sydney onto the sea. And in the late afternoon, when the sun was setting, the rays of the sun would cast off of the sea and produce an interference pattern, the shimmering. And by studying that interference pattern, they were able to resolve sunspots. And so this was very significant in radio astronomy because it was the first time that we could do anything approaching a high angular resolution. So we'll get to this question of angular resolution in a bit, but in short, angular resolution is very important for astronomy. Next, so after the war, they developed two very fruitful and productive groups studying radio astronomy in the UK. The first group was based in Cambridge, and it was headed by Sir Martin Ryle. That group went on to found the Mallard Radio Astronomy Observatory outside Cambridge. In 1946, they built the Cambridge Interferometry with Anthony Hewish, and using that, they published the first radio interferometric measurements of the sky. So in the picture there, you can see Martin Ryle and two of his interferometer dishes. There were four of them. In 1959, he led the 3C catalogue, which is still a very important and well-known catalogue of sources in the sky. And in 1974, he won a Nobel Prize for his pioneering of aperture synthesis. So the Cambridge group went in the interferometry route. The second group was at University of Manchester, and they went more of the single dish route. That group was led by Sir Bernard Lovell, and he was originally a cosmic ray researcher at the University of Manchester. And in 1945, he established Jodrell Bank Observatory. In 1957, they started construction on the 76-meter Lovell telescope, pictured there, which was at the time the biggest radio telescope in the world. I believe is still third largest single dish radio telescope in the world, if I'm not mistaken. And this is quite important for us in South Africa, of course, because the headquarters of the SKA is based at Jodrell Bank. So if you continue any work with SKA, you'll be sure to work with people from Jodrell Bank. Right, so that concludes my tour of the big names in radio astronomy in the 20th century. It also, those few decades after the 40s also were very fruitful in terms of a number of very important discoveries. Radio galaxies were found for the first time in the 1940s to 50s. Martin Ryle and his group found quasars in the late 1950s. Penzias and Wilson studied for the first time or discovered the cosmic microwave background in 65. Masers were also discovered in 65 by Weaver et al. And Jocelyn Bell and Anthony Hewish discovered pulsars in 1967 at Mallard Observatory. So there have been, in all, there have been 8 Nobel Prize winners come in from the world of radio astronomy. In 74, Martin Ryle and Anthony Hewish won, Ryle for pioneering aperture synthesis and Hewish for discovering pulsars. In 78, Penzias and Wilson won for discovering the CMB. In 93, Holst and Taylor won for using observations of a binary pulsar to test general theory of relativity. And then in 2006, the most recent one was Smoot and Mather, one for some studies of the cosmic microwave background. Right. So that's my very quick crash course on the history of radio astronomy. Next, let's enter into some discussion of some of the fundamental questions that radio astronomy seeks to answer. So the first question that we have to ask is why do we have to define something like radio astronomy? In astronomy, we like to divide the spectrum up into different pieces. We say there's gamma ray astronomy and X-ray astronomy and optical astronomy and radio astronomy, and oftentimes the astronomers studying those different fields of a kind of friendly competition between them. Why do we make this distinction? Because a photon doesn't know if it's a radio photon or a gamma ray photon. So this distinction is entirely a man-made thing. It's an artificial thing that we impose on nature, but it's for a good reason. It's for practical reasons. And a big motivator for that is the fact that there's a gap in the atmosphere that allows us to observe radio waves from the Earth. So this illustration on the bottom of the page shows the atmospheric opacity at different wavelengths. And you can see that gamma rays and X-rays and ultraviolet light are pretty much entirely blocked out. Then there's a bit of a gap for visible light and some near infrared. Most of the infrared spectrum is absorbed by atmospheric gases. You can think about the greenhouse effect for that as well. Then there's this nice gap for radio waves, where we can build ground-based radio telescopes. If you want to observe gamma rays, X-rays, or infrared, you really need to put a satellite into space and observe from there, which is much, much more expensive and technologically prohibitive. So that's one reason. A second reason is that in radio waves, we can use what are called wave regime techniques, meaning that we can regard the radiation that we observe as continuous electromagnetic waves rather than discrete photons. If you ever get involved in gamma ray or X-ray astronomy, you know that the number of gamma ray and X-ray photons are so few, you don't really conceive of them as electromagnetic waves. You count individual photons. So that's a whole completely different ball game from radio waves. Also, because we are operating in a wave regime, we can do clever tricks like interferometry in radio, which is much more difficult to do if it's possible at higher energies. Another important fact about detection is that we can manipulate radio waves. So we can bounce them off of a metal dish and focus them onto a receiver. That's how a typical radio dish works. Whereas with X-rays and gamma rays and the like, those photons just pass right through metal, right? So you have to devise a completely different detection strategy. So typically in X-ray and gamma ray telescopes, they have layers of like metal thin sheets of conductive metal, and then when a photon goes through those sheets, you measure the electric current that it causes on those sheets. So and then you try to reconstruct more or less where the photon came from. So it's a completely different regime that you're working in. And then the third big reason why we want to have something like radio astronomy is because different processes working in the world, in the universe, produce different wavelengths of radiation. So, as we've already seen, thermal processes from hot objects tend to produce light in the optical regime. Other non-thermal emission processes, synchrotron radiation, curvature radiation, masers, um, Compton scattering, all of them produce emission at different wavelengths. And so to get a complete picture of whatever object or region of the sky that we are observing, you have to cover as much as possible the electromagnetic spectrum. Right, so let's talk a bit about these processes, these emission processes. In lecture 4, I believe, we're going to go into detail on the different emission processes that produce radio emission. But today I just want to introduce a very important distinction that we make in astronomy between thermal emission and non-thermal emission. So thermal emission is emission caused by exactly what it sounds like, the temperature of some body or some assembly of particles that have a certain distribution of temperatures that cause a emission in a black body spectrum. And the peak of that emission is inversely proportional to the temperature of the emitter. So in the optical regime, we can see objects that are as hot as 3,000 to 10,000 Kelvin. So that means that we can see in visible light, we can see stars and clusters and galaxies. We can also see ionized gas, the forms of nebulae. And on the cooler range of that, we can also see planets and moons, which don't produce their own thermal emission, but reflect light from stars. In radio emission, as we said before, the temperature to see thermal emission in radio has to be very, very low. So we don't see typically stars and these hot objects, but we can see the cosmic microwave background that has a temperature of 2.73 Kelvin, which means it peaks at about 220 gigahertz. And we can also see some spectral line emission from the cold interstellar gas that includes the famous H1 line. And then if you have a sensitive enough radio telescope, we can actually see some of the very bright stars and planets. So on the right, there's an image of I think it's Jupiter in radio waves. But in general, in radio astronomy, we tend to observe non-thermal emission. So that's emission produced by other mechanisms that typically involve accelerating particles to relativistic speeds, and then those particles emit light in the radio wavelengths. And they have those emissions have a very different spectrum from blackbody emitters. So on the right, you can see a plot of the spectrum. That's the flux against wavelength of various emitters. So you can see the Sun and the Orion Nebula. Both of those are thermal emitters, and they look very different from these other emitters, Cas A, Crab Nebula, M31, 3C273, which are all non-thermal emitters, and they display these what we call power law spectra. So it's basically an exponential process. If you plot it on a log-log scale like this, it's a straight line. It's called power law distribution. And if you look at the plot at the bottom, you can see this is the typical kind of spectrum that you expect at different wavelength regimes. The radio emission is more or less power law distributed. The CMB follows a very nice, very, very precise black body distribution. Infrared and far infrared and near infrared also have similar kind of black body-esque spectra. And then at X-ray and gamma rays, they have kind of weird spectra. I think often that involves Compton scattering. That's why they look so weird, I believe. So I've listed a number of objects that emit these non-thermal emissions. So radio galaxies, quasars, masers from interstellar molecules, coherent emission from neutron stars. We can observe cosmic rays indirectly through the shower of emission that they emit when they enter the atmosphere. And we can also observe gravitational waves indirectly through the interaction with pulsars. Why radio astronomy? Here I'm listing a number of different kind of hot topics that are that exist in science at the moment that radio astronomy can help with. One of the things that you can do is you can study the so-called dark ages, the very, very early stages of the universe, try to understand why photons and baryons decoupled from one another. You can study the epoch of reionization by looking at highly redshifted 21 centimeter lines. So that's the early stage of the universe when stars and galaxies just started to be formed. You can study the formation of those early structures by studying high redshift radio galaxies. You can study the evolution of the universe on a large scale by studying diffuse emission. You can look at how dark matter and dark energy might evolve by looking at clusters of galaxies and stars. AGN, looking at active galactic nuclei, can tell us something about how energy gets injected into the intracluster medium. It can also tell you a bit about how black holes are formed and how they grow. We can study the accelerations of particles to relativistic speeds by studying AGN and merger and accretion shocks of clusters. You can study formation of stars and galaxy evolution by looking at distant starburst galaxies. If you look at some nearby galaxies, you can study how magnetic fields form in the universe and how they propagate. And then you can do these big all sky surveys, meaning you look at the whole sky to try to understand the different populations of different sources and how they work and how they form. So these are just some of the big questions that radio astronomy can help us answer. Let's move on to our next question, which is, so we've just defined radio astronomy, but why do we want to do aperture synthesis? So aperture synthesis, in case you don't know, means instead of having one dish, one receiver receiving a radio signal, you have multiple different antenna elements, each receiving that signal some distance apart, and then adding those signals together in such a way that it could approximate one huge telescope. So Meerkat is an example of a aperture synthesis telescope. The reason why we want to do aperture synthesis again comes down to the question of uh, angular resolution. Angular resolution means how fine of details can we make out precisely in a portion of sky. Um, and that's very important because in a given region of sky, there might be many different sources that could be responsible for any element of emission. So it helps to be able to say precisely what galaxy or what part of a galaxy produces some emission. With single dish telescopes, the resolution of the telescope is approximately equal to the wavelength of the emission divided by the diameter of the dish. So at optical wavelengths, which are short wavelengths, you get angular resolutions of about 1 arc second quite easily. But at radio wavelengths, which are longer than a centimeter, at 1.4 gigahertz, you would have to build a radio telescope of 57 kilometers wide to get that 1 arc second resolution. And matching that resolution of optical astronomy is very important because if you want to compare radio observations and optical observations, you need to have matching, more or less similar um, angular resolution. Because say you make some discovery or you observe some source in the radio, if you want to compare that to a known optical galaxy in that field, there might be a number of optical sources that match your radio observation, and so to pinpoint exactly where your radio emission is coming from, it's very important to have a sufficient angular resolution. So with interferometer arrays, we sidestep that problem. We don't have to build a huge dish of kilometers wide. Instead, we build a number separated by a baseline. This capital B is called the baseline. And that's the distance, the maximum distance between two array elements. And now the angular resolution becomes approximately equal to the wavelength divided by the maximum baseline. So we can have baselines kilometers apart and thereby get close to our arc-second resolution goal. In terms of sensitivity, the sensitivity of the telescope is proportional to the gain. That's the capital G that I wrote there. And that's proportional to the effective collecting area of the telescope. So the more collecting area, the bigger the dish, the more gain you have, the more sensitivity the telescope has, the fainter object it's able to see. In an interferometer array, the same equation holds, but now you add up the effective area of all the different array elements. So it's much more feasible to build 64 1-meter dishes than it is to build one 64-meter dish. In addition to that, you can always upgrade the sensitivity of the telescope by building more and more of these dishes. And then thirdly is the question of the field of view of the telescope. So the field of view of the telescope is the area on the sky that you're able to see at once, and that's proportional to the square of the resolution, basically. And again, that's inversely proportional to the diameter. So you want to build a big dish to have a fine resolution and a big sensitivity, but the bigger that you build it, the smaller that the area on the sky is that you can observe at a given time. And that means if you're trying to do surveys for that any survey that's going to be untargeted or that is all sky is going to take longer and longer because you have to move that small beam across the sky very slowly. The bigger the beam that you have, the quicker it's going to be, more efficient it's going to be to cover the whole sky. Um, with an interferometer, the field of view is proportional to the area, or inversely proportional to the diameter of one dish. So if you have an array of 1 meter dishes, it has a field of view of a small dish, but with the sensitivity and um, angular resolution of a big dish. So these three factors combined mean that the next generation of radio telescopes are all pretty much interferometry based. Um, and that's the next, yeah, that's why the SKA era is going to be so exciting. Um, Finally, let's get into some basics of radio signals. With this section, I want to introduce some of the most important quantities that we're going to use in the rest of the lecture series. Um, One important quantity is flux and flux density. So flux is a measure of the rate at which the energy of a signal crosses perpendicular to some area. So it's a rate of energy per area. It's given in units of watt per square meter per hertz. And we usually measure that in units of Jansky. So to give you some notion of this, on the plot in the middle there shows the flux of different objects at different frequencies. So if we look at the typical radio frequency around the 21 centimeter line, the Milky Way has a radio flux of about 10,000 to 100,000 Jansky. Meanwhile, pulsars tend to have a flux of about a Jansky to maybe a few tens of Janskys. Oftentimes, fluxes are quoted in terms of flux density. So that's the flux divided by unit frequency. So in fact, the Jansky is a measure of flux density, not flux. Sorry about that. In the table on the right is a conversion table between the different visual bands, their wavelength, and what the flux density would have to be at a magnitude of 0. So that's a useful conversion table to have in mind. Power is another important quantity. That's the flux from the radio signal multiplied by the effective area of the telescope, and that's measured in watts. The gain of the telescope is a quantity proportional to the effective area of the telescope, as we've said before. So that's a handy way of quantifying the sensitivity of a telescope, and it's given in Kelvin per Jansky. The brightness or intensity of a source is to get the flux, you have to integrate the brightness or intensity over a solid angle and over a frequency range. So it's measured in Jansky per steradian. If you're not familiar with the concept of a steradian, it's like a radian. A circle is divided into 2 pi radians, right? A sphere is divided into 4 pi steradian. And you can see an image of what one steradian looks like. Then the next important equation is the radiometer equation, and that gives you some estimate for the minimum flux that you're able to observe above a certain signal to noise ratio. So you set a limit above which the signal to noise ratio has to be to count as a detection of a source, and then the minimum flux that you're able to um, uh, observe depends on the system temperature. We'll get to that in a second. It's inversely proportional to the gain, so the higher the gain is, the lower this flux density minimum is going to be, meaning the more sensitive the telescope is. Uh, uh, it's also inversely proportional to the number of polarization channels. So usually for full polarization observation, you take 4 polarization channels corresponding to the 4 Stokes parameters. I'll talk about the Stokes parameters as well in a bit. It's inversely proportional to the integration time. So the longer that you integrate your observation, the higher sensitivity your image is going to have, the finer details you are able to pick out. And it's also inversely proportional to the bandwidth of the telescope, the frequency range over which you're observing. So in other words, to build the most sensitive radio telescope, the things that are within your control are to minimize the system noise, which means to have as little noise in the system as possible, to maximize the collecting area of the telescope. So in an interferometer, that means maximizing the number of dishes that you add together, and then to maximize the bandwidth that you're working with. So observing over as wide a range of frequencies as you can. So let's talk about quickly about that concept of temperature. This diagram shows possibly the most simple depiction of how a radio telescope system works. If you have the receiver of the antenna is enclosed together with a black body emitting at temperature T, so it takes in a signal with power corresponding to the black body temperature. That signal gets transmitted, usually using a waveguide or nowadays a fiber optic cable, and it gets transmitted to a filter that removes frequencies above and below certain values. So that's a band pass filter. You want to limit the frequencies within the signal to a certain range. And then it gets transmitted further. At the end of the system is some resistor or some resistive load that matches the impedance of the system, and by second law of thermodynamics, if all of this is in thermal equilibrium, the temperature of that resistor would be equal to the black body temperature of the source. So based on this very simple picture, we can define something called the system temperature, which is the temperature of the resistor that you would need to match the power of the signal generator at the receiver. Then the brightness temperature, it means if you are observing some source in the sky, means what temperature a black body would need in order to match that power. And similarly, we can define something called the noise temperature, which is the contribution of the noise generated by the receiver to that measured temperature. So all of this together means that in a very real sense, the job of a radio astronomer can be conceived of as taking the temperature of the sky at a certain position at very fine intervals and comparing that to the temperature of your system. And if the temperature of the source is higher than temperature of your system, that means you can that's a positive discovery or positive observation. Right, so let's talk a bit about electromagnetic waves. We've already seen from the Maxwell equations that the solution, the general solution to the Maxwell equations is in the form of these traveling sine and cosine waves. This is one way of writing the equation for the electric field, the oscillating field. In this simple plane wave approximation or case, the electric field is oscillating in a direction A. So that's perpendicular to the direction of travel. It's the direction in which the electric field is oscillating. And if that direction is constant, if it's not moving around, that means that the signal is linearly polarized. So in other words, the polarization is always defined in terms of the direction of the electric field. If that angle of polarization is changing, we can define this equation in terms of values Ex and Ey. And if Ex is equal to Ey, in other words, as you can see in the picture, the plane of polarization is turning in a circle. In this case, it's turning clockwise, so that's called right-hand polarization. If Ex equals Ey, that's called circular polarization. So linear polarization and circular polarization are edge cases of polarization. In general, waves will have a mix between linear and circular polarization, and we call that elliptical polarization. So this is a depiction of a typical elliptical polarization. The ellipse there describes the rotation of the plane of electric and magnetic fields, and we can describe that ellipse using major and minor axes, A and EB in this case, and then an angle beta. If that angle beta is equal to plus or minus pi over 4, that corresponds to circular polarization. Otherwise, we can define the Stokes parameters, I, Q, U, and V. I is the amplitude of that oscillation squared, and that measures the total intensity of the wave. And then you have these quantities Q, U, and V measuring different cosine and sine products of these two components. So oftentimes it's more useful to talk about the ratios of these different parameters. The V parameter corresponds to the ellipticity of the polarization plane. So if V is 0, that I believe that means that it's entirely linearly polarized. If V is equal to E0 squared, so if it's equal to I, that means it's entirely circularly polarized. And then the ratio of Q to U determines the orientation of the rotation of the polarization plane. And if you add the Q, U, and V Stokes parameters in quadrature, that gives you the square of the total intensity. So telescopes like Meerkat typically record in 4 polarization channels, each one corresponding to a Stokes parameter, and then it records the flux of the signal in each frequency channel in each of these different parameters. Right, so that's it from me for today. Uh, I'll talk about the rest of the lecture series in a bit, but before that, are there any questions?
Raul has his hand up.
Okay, Raoul?
Hi, so tell me, what would happen if the baselines were not the same? Like, let's say you had a telescope, like one telescope was 100 meters apart from another telescope, and the same telescope was 50 meters apart from another telescope. What happens if the
Yeah.
baselines were the same?
Yes, that's a very good thing. In general, we want for a radio telescope, we want a mix of different baseline lengths. So the longer baselines allow us to resolve the finer details of an image, so that let us see the very small parts of the sky. And then the shorter baselines allow us to resolve the large scale structure of the image. So in general, you want to have a mix of short and long baselines so that you can resolve the full thing. Or if you want to observe for a particular purpose, if you only want to look at the broad scale structure, then you can use only the shorter baselines. When we talk about in detail about radio interferometry later in the lecture series, we'll get to explaining how this works in the UV space. You want to basically fill out different regions of the UV plane. But for now, it's enough to understand. You generally want a mix of different baselines, and different telescopes have different strategies for arranging the baselines in different shapes that they think will suit different types of observations.
Thank you, sir. I also have another question. Like, do the astronomers like they choose the baseline sequentially, or is it random?
Uh, so do you mean how do they choose which baselines to include in their observation?
Yes, sir. Is it done in a sequence or is it done randomly?
Oh, yeah, no, you can use any combination of baselines that you would like to use. There's no sequence that it needs to obey. Again, depending on your specific purposes for your observation, you might want to include longer or shorter baselines, but that's pretty much up to the astronomer. It's all pretty dynamic in that way.
Okay, so
Yeah, so
if
sorry, can I comment on that?
Yes, of course.
Yeah, during observation, you have no control on the baseline. Can you hear me?
Yes, yes, we can hear you.
Okay. Um, so what happens is all the telescopes point to the source, all the visibilities. Can you hear me? From Jude. Jude, can you mute? Yeah. So all the telescopes will point to the source. Each of the data arriving in the telescope goes to the correlator, which is a supercomputer that puts together, that computes the correlation between each two antennas. So at the correlation stage, there is no ordering of the visibilities. The visibilities is just a data point that gives information contained in one baseline, which is two antennas. However, in some cases, especially in VLBI cases, when you do the calibration steps, you may need to order the visibilities according to time and baseline. For compact array, this is usually a very trivial step. For VLBI, where the baseline lengths run into thousands of kilometers, then there is, to some extent, some need to order in time and baseline. Okay. Maybe what Ian will still mention later on, which in interferometry adds one other layer of complexity, is when you have a heterogeneous array. With the meerkats, it's a homogeneous array where all the dishes are the same size, right? So it means if you draw a circle for one dish, or what it sees in the sky when it points to a certain direction is the same size of circle for all the dishes because they are all same sizes. For heterogeneous dishes where one dish is smaller, another one is bigger, then they're not seeing just the same size or the same area of the sky, but you still have to combine the data anyways. Tian, I'm not sure if that is in your slide. Probably should be discussed when you talk about interferometry.
Yes, definitely. Okay, thanks. Thanks for that chance. Any other questions?
Yes.
Yeah, maybe just a comment. That's a really in-depth history of radio astronomy. Thanks for that.
Yeah, I spent a lot of time, but it was quite fun reading about that.
Yeah. Cool.
Raoul, I think you maybe had something.
Yes, I just wanted to know, like, back to Professor James' comment. So, what I just wanted to like what you were trying to say, like, you're trying to say like all the signals that come into the telescopes, like they go into the computer, and then they are combined.
Yes.
Okay. So everything is combined from every telescope.
Yes. So, I'm not sure if Tian will cover this again.
Yeah, sure.
Every data point that comes from an interferometric observation needs to be cross-correlated. So if you learn calibration and imaging at any point where you use CASA or APES or anything else, one of the steps you carry out is to flag autocorrelation. Autocorrelation data is similar to single dish data. It's like data coming from a single telescope. So if the computer fails to correlate any data point, then you want to take it out because it's not going to give you baseline information, which is what you need. So essentially, what you do in the correlator is that the two antennas are separated by a certain distance. It doesn't matter how small, even if it's just 10 meters apart, the time of arrival of the signal from a source to each of the two antennas will be different. So at the correlation spot, you're essentially removing the time delay and then combining the data. Okay, so I see Tian is showing that this will be explained.
Yes.
Yeah.
So from lecture 6, 7, 8, we're going to cover all of this. How a radio telescope works, the correlator, the UV coverage, all of that. We'll cover that.
Okay, okay, I know it's coming up, but does that mean that the correlator and the time delays, can they not be covered by the fact that one does what do you call this thing again? One does integration for 10 minutes, for instance. But how accurate does that time, does that correlation have to be in terms of in terms of the timing itself? Should it be like exact to 0.001 of a second, or is there a number that is deemed sufficiently well correlated?
Tian, if you want me to answer, I can go ahead.
Yeah, do you know an answer?
Yeah. So, Zolile, you're talking about the total integration time, which is what you would do if you want to detect a very faint source, right? You still
Yes.
want to integrate over a long time.
Yes.
That is not smeared out in interferometry. So in interferometry, like in meerkats, there is a measure clock that has timing accuracy of 1/1 billionth of a second. That's 1 nanosecond. And
Yeah.
that's we call it PPS signal, is distributed to all the antennas.
Okay.
So what is happening is you may be integrating for 8 hours on a source, including your calibrators that you will drive the antenna and integrate maybe for 2 minutes, you come back to your source.
Yeah.
Each of the signal coming in is clocked by a
So within a
nanosecond scale.
nanosecond.
Yes, otherwise you cannot correlate the data. So you correlate with that clocked signal. Of course, you can now average, assuming the person proposing says, yes, you will clock my signal to nanoseconds accuracy, but I don't need that. Fine, I'm not doing pulsars where I need microsecond or millisecond to time the pulsar. I'm just making continuum imaging. So I want each data point you drop for me to be averaging 8 seconds. So you clock the nanoseconds, all of them correlate, and you take each 8 seconds block and you average it into one.
Sure.
And then it's every 8 seconds data that the PI receives for 8 hours, which they can now image and average.
Oh, okay. So you don't. Oh, we'll talk about that later. So you track the source
Yes.
for 8 second spurts, or you let it smear and taking all of those 1 second integrations and essentially stacking them.
Good. So we call the 8 seconds that I mentioned now dump rate.
Okay, dump rate.
The dump rate, yeah, DUMP. So
yeah.
if you dump 8 seconds of a data, then you cannot correlate it if you dump it just from the timestamp, right?
Okay.
So it means what we do is the first timing is the clocking of the signal as they arrive using your meter clock.
Okay.
The next is to correlate the signal with the clocked signal because we're trying to remove the time difference.
Okay.
Then the next is to check what the PI has requested. If it's Tian asking for 0.1 microseconds timing, then we don't average. So if it's someone else who is doing continuum image, then after the correlation, you take each of those nanosecond signal times how many times you need to get 8 seconds, and then you average all of them and call it one data point.
8 billion of them. Okay.
Yes.
All right.
So
okay,
you do that for as many for the full time that total integration time that the PI has requested. So the highest time resolution, assuming there is a transient event during the observation, and the transient happened just in 1 second, and you have already averaged 8 seconds, then you might miss it out.
You are going to miss it.
Yeah.
You have to do delay calibration as well between every couple of observations, right?
Sorry?
You have to do delay calibration or phase calibration, sorry. Make sure that the
so
phases
each observation has a overhead, and the overhead includes that you need to make sure that the telescopes are getting fringes. So you point to a first delay calibrator, and then you point to a phase calibrator. The phase calibrator just is typically for you to use and pin down the position where the antennas are pointing. So it's mostly for positioning. And then you need something to scale the fluxes of the source. For compact array, yes. For VLBI, it's useless because they can't really calibrate fluxes. So you need to point to a source with a known flux and then use it to scale your own So yeah, there is calibration. I think Tian will address those.
Yes, for sure.
Thank you.
Cool. Any other questions before we go?
Yeah, maybe just as a comment, it would be nice for each of the students to probably read the material before attending, because there are a bit more depth in the textbook which you can extract, and then when you listen to the lectures, it will make more sense.
Definitely.
And thanks, Tian, for getting on top of this.
No problem. So the next lecture we'll have a bit of a break. I'm going away on a couple of meetings in a row, and there's IAUGA. So the next lecture is only scheduled for 23rd of August, which is in another while. But yeah, I'll communicate the reading for that beforehand. Okay. Any last words?
Travel safely.
Thanks you too as well.
Bon voyage. Yeah, okay.
Okay. Yeah, I think then we'll see one another on Tuesday, is it, for the practice sessions? Yeah. Okay. Cheers, everyone.
All right.
Bye-bye.
Bye, everyone.